Today I'd like to give you a concept of we call the system type. The content today is not covered in our textbook, so I'm going to write down on board slowly. But the concept is very straightforward. It's this. Just like I described, if a system is slow by nature, for example, elephant, if you like the elephant to do a agile action response, they never can do it because the system is just so slow and so slow. So if you like to have the slow system follow up the fast changing signal, then you can see basically the system just fall behind more and more. Eventually, the discrepancy go to infinity at the steady state. Okay, so that's the concept. Slow system won't be able to catch up the fast command. On the other side, the fast system, which means the system can respond very agilely, very quickly, will be able to always to catch up and meet the slow command. For example, if the system is so agile, then if the command is changing over time is very slow, then the system by its nature will be able to catch up this signal very quickly. So eventually, you can expect the steady state error should be equal to 0 because system is going to catch up the signal. Okay. All kinds of the systems have its momentum. Has its inertia, even for the electrical system. So you have to overcome the inertia to get started, accumulate momentum, and then you come up with the chasing whatever the signal is. So basically, the momentum and the inertia determine how the system stubborn is or not. Again, the fast system will be able to chase, to follow up the fast command. Okay. So the concept is I want to give you the introduction of the system type. And this one doesn't appear in our textbook. So type of a system simply is to define how system slow or fast. Type 0 system is the slowest system. Type 1 is a little bit faster. Type 2 is faster than type 1, and etc. So for type 1 system, so for type 1, again, type of the signal, the same thing. Type 0 system is slow command, and type 1 system is a little bit changing faster over time. So in this way, the type 0 system, which is a slowest system won't be able to catch up the type 1 signal. Okay, because the type 1 signal is changing over time is faster than the slow system. So eventually they would have the steady state error will be getting larger and larger for the infinity. Okay, so here I give you the definitions. So let me use the one example to demonstrate the concept. And there's a no, let me use this example to demonstrate, and then let me explain how the real practice is. So here we consider it is a unitary feedback system. So for these systems, here let me calculate the aerodynamics. Okay, so now this using these simple examples, we can have the template forms to calculate the steady state error. And that is, basically you can see that is determined by R of S and G of S. So with this in mind, we can begin to, so here, the value of ESS is determined by RS and GS. Okay. So here the contents of RS and GS will be analyzed. I'm going to tabulate throughout the whole thing here. So, for example, we consider is the RS is the step input. Then we can calculate the ESS here. Here I want to use the type 1, type 0, and type 2, and I will give you definitions. So what is type 0 systems? And for example, if GS is equal to, let me make one example, K times 1 plus S, and S plus 1, S say plus 1 plus 2S, or anything. So this is called a type 1 system. And let me make one example later you to make conclusion. If K 1 plus 2S, S squared, S plus 1, S plus 2, so this is called a type 2 system. And for example, GS, maybe I put it here. So GS here is, for example, K 1 plus 2S, S plus 1, S plus 2. So this is called a type 0 system. So are you able to make conclude how to define the type of a system? By looking at the 3 examples here.
Oh, S.
S, right? So basically here the type 2 system is such that you have double poles at 0 at the origins. For type 1 system, you have single pole at origin. And for type 0 system, you simply have no poles at the origins. So here, continuously, if we continue to write it up, say type 3 would be something. So here would be other certain polynomials, say S plus 1, S plus 2, say K, 1 plus 2S, etc. Okay? So from here, you should be able to deduce the information. So again, we're back to here. So if that would be the type 0 system, so like this one. So we can do the calculations. So per this equation, so here is our scratch. How about that? Scratch pad. So right now, if GS is type 0 system, so type 0 system, you can see when we plug in S equal to 0 there, so that is, okay, so limit as approaching to 0 as R of S 1 plus GS. Okay, that's our calculations. So right now, this we simply put the S equal to 0 as, and for this case, R is the step input as over 1 we introduce here. Then 1 plus, okay, what is the G value of 0? When G is type 0, then we're looking for this term. Okay, so we plug in S equal to 0 to type 0 system, then that should be certain constant value, say let me call it Kp. And Kp is a constant. Mine is not a 0 constant, right? Okay, so in this way, let me define, let me define, okay, so whatever. So this should be a non-zero constant. Let me say whatever here. So here should be, say, 1 plus Kp. So which is not 0. So here, by definition, what is Kp? Kp is a certain non-zero constant. Okay. So if you like, you can make your own note. Kp is a certain non-constant, non-zero constant here. Okay. And now we look at the type 1. For type 1 system, and again, right now we determine this value here. For type 1 system, we plug in for type 1 system, which means right now we're going to calculate is the G value at 0. So for this case, you can see when S equals 0, then the G value is how much? Infinity. So it's 1 plus infinity, right? So here is how much? It is 0. Any questions? Are we okay? Yes. Any questions about these calculations?
Why is it infinity?
Why is infinity again? Right now here we're going to calculate is this. Let me do this again. So this value simply is equal to as multiplied as over 1 plus limit as approaching to 0 of G0, GS, right? Okay, so this one will be becoming equal to 1 plus. What is this?
Type 1
For type 1 system, we simply calculate the limit of as equal to 0 of this term. All right? So that is infinity. Right? We calculate the value of this for x equal to 0 because of the 1s at the region here. Okay? Okay, so here is going to 0. For type 2 system, the same thing. For type 2 system, right now we even have a double poles and region, so that is more infinity. So here again, this one will be infinity here. Oh. Yes. So from here you can see, by here, I've told you before we do the calculation, type 0 is the slowest one, and higher types, that means the dynamics of the system is faster. So here we have a certain command. Here is a unit step input here. For type 0 system, without going to do the details, I don't know what's going on here, but for type 0 system, maybe here transition, I'm not sure, but for sure is at the steady state error. At the steady state, they have the discrepancies, and it's given by this number. So these are type 0 system, the features. For type 1 system and type 2 systems, I don't know what's going on here, but for sure a steady state error is here. So that is type 1 or higher. So this is type 0 system. Okay. So lower order systems, the lower type system, which means the system type, the system dynamics is slow. So in this case, for the type 0 system, we can see it is unable to catch up the step input command. So even this command is constant over time, the system is still not able to catch it up perpetually. It's all still fall behind. For type 1 system, is able to catch it up. Okay. So the same thing in a similar way, this is called the type of the systems, G1, GS. And for this one, we can have the similar definition. We can call this is the type 1 signal or type 1 command. For type 1, for the type 1 system, is able to catch up the type 1 command, just like given by this table here. Okay. So with this one, then we can look into the even higher system. So now we look for the when RS equal to S squared. So this is the length. So that is time. So we have this, and the same thing we can calculate the type 0 system, type 1, type 2. So here, before we're doing this, anyone can make quick conclusions here. Before we do the calculation, and again, the slower system won't be able to catch up the fast signals. This signal is changing over time even faster than this one, right? So for sure, if type 1 wouldn't be able to catch up, then this will never get it. And type 1 is kind of a doubt, and here we might assume this one may be able, maybe have a discrepancy. So here we do the calculation again. So for this case, we want to calculate is, again, here is our scratch pad. And we want to do the calculations as approaching to 0. And as multiplied with right now in terms of template, our input R is S squared. Okay, that is different from the previous one. Then here is 1 plus GS. Okay, so we do these simplifications here. So S equal to 0. So here on the numerators, we have 1 over S left. So here, let me put the S into the, multiply into the denominator here. Okay? Okay, so with these things, then we can continue. So basically this is 1, and when S approaching to 0, basically this is 0. So here it becomes limit S approaching to 0, S multiplied with GS, right? Because this value equal to 0. So now we only focus on this term. So again, for type 0 system is like this. For type 0, GS is, for type 0 system, GS will be something like K, and I make one example, okay? Basically, there's a no pulse at the origin. So when S times GS, then that will be equal to Sk S plus 1. So when this value is taking S equal to 0, then you can see this value equal to how much will be equal to 0, right? So basically in this calculation we can see, using one example, this one basically is 1 divided by 0, right? So this is going to infinity, which means the slowest type of the system, type 0 system, if we want to use the element to catch up this kind of time changing, the linear time varying system, it's always fall behind, and then discrepancies is getting larger and larger over time. Eventually, it's going to infinity. Right? You got a feeling? For type 1, here let me change in things. Again, here is our scratch. For type 1 here, we simply added our one more S here, right? Okay, here for type 1 system, basically from previous one, I simply add one S here. So here, I simply one S here, okay? So from here, you can see we can cancel this. So for type 1 system, what we have is this, a certain constant, let me call it KB, whatever the constant. So here is 1 divided by KB, and which is non-zero. So here, using type 1 system to change the type 2 signal, it's almost there, but still remain discrepancies perpetually. So which means just like running, you run slow initially, and you try to chase the elite athlete. Eventually, you just lose because he can start up very quickly. You are slow. But when you come up with the momentum, your momentum, you can maintain the same speed with that elite runner. You always fall behind by 10 meters to the end. The 10 meter is called because you are so, just like me, really fast starter. So initially, the overcome the inertia is slow. You got a feeling? Okay, so if some, I know, some of you here are athletes, swimmers, runners. Rifle is a different rifle. Yeah, it really, that is using the human rifle is you need actually rifle, the shooting is harder. You need to stabilize your breathing, right? So yeah, rifle shooting is harder, but sorry, I couldn't utilize that. Okay, so here is the one. So from here, you should expect type 2 should be equal to 0, but we can do this calculation. So for type 2 here, allow me to use the board here for type 2. So here we simply have the 2 zeros at the origin. Sorry, 2 poles at the origin. So here is S2, S squared. So once this coming out, so basically this is, we cancel it, we have 1s at 0, so that is infinity here. Okay? So for type 2, here is 1 divided by infinity, so here is 0. Which means for the type 2 system, which by nature is dynamics, by nature is very fast, so it will be able to catch up this command, and without any fall behind, you can precisely follow up this command in the finite period of time. So that means steady state error is 0. Okay. So we can move on to the next one for one more example here. So here, for example, let's say Rs is time and this is R2. So for example, if say this is a parabolic, okay, so which means say RT will be equal to T squared.
2 over S cubed.
I forgot the,
2 over S cubed.
right? Is this? Is that this? One.
Wait, wouldn't it be 1/2?
What is this?
That would be T squared over 2.
T squared over 2. Okay. Sorry.
Yeah, because it's 1/2. Yeah.
Yeah. So I want to make is this one. Okay. Thank you. So again, this is the GS, and this is steady state error here. So here again we have type 0, type one type. Okay, now we can do the calculations here. So again, we start from here. So here right now we have is for the 3 here is we simply plug in here.